Yeah. Okay. So I had this very fancy title generated for me by ChatGPT, but honestly, it's more about how we can take these raw video, football videos or the sports that we record and turn them into something that the user wants to look at and they can get some insights from and they can show it to their friends and so on. So it's supposed to be a social fun thing that you can look at, but also something that can provide you with some data depending on kind of how pro level you want to take it. Yeah, but just a brief introduction about me. Yeah, I just mentioned I live in Copenhagen now. I have a background in mechanical engineering and data science, and a few years back I used to work for Codon, but now I'm working as a machine learning researcher at VU. And I also just briefly wanted to introduce kind of VU and the product because it's quite a fundamental to how we also do the AI and machine learning related stuff. So I think this kind of description of that it's a portable video solution that automatically captures, analyzes, and streams your matches is quite correct because yeah, it's a camera you can move around from field to field. It's battery powered. Yeah, you turn it on, you can capture a match. It gets uploaded to the cloud where we do a bunch of post processing analysis, but you can also stream it directly to both YouTube and other platforms. But the story so far is that it was founded roughly 10 years ago now. And what you see here on the left is the first mock-up they had, which is just a foosball paper with some GoPros mounted. And then they released the first camera in 2019, which was this quite sturdy kind of 3D printed casing. But as you can see, the cameras have kind of evolved, gotten bigger lenses and more resistant and waterproof and so on. And we released the latest version last year, which has two 4K cameras. We've also had quite a bit of growth in the recorded matches. So we have we started with roughly 40,000 back in 2019, and now we're up to 2 million. And I think if we had the latest numbers for 2024, I think we have them. I think they weren't included in the slide, but it's around 4 million. So really, we're recording a lot of football matches each year. And also all of those matches are around like 1 hour, maybe 2 hours on average. So it's a lot of data to have collected on the cloud. We mainly focus on football, but we also have support, like all the most advanced features are for football, but we have the basic kind of packages also available for basketball, volleyball, lacrosse, and hockey, and so on. So a bit about the data processing. So actually, if you take these like this raw video stream, there's a lot of data in it, and if you don't do anything smart about how you process it and encode it and store it, then you'll end up with almost 3 terabytes per match. And obviously, you don't want to pay the cloud storage cost for that. So we do a bunch of post processing. We have a whole team kind of dedicated to that. So I don't know all the specifics of how it happens, but in the end, you can end up with this. So there are 2 lenses, so you kind of get 2 4K streams, and we take around 11 gigabytes a match. But still, you can kind of do the math yourself. If you have several million recordings, that turns out to be a lot of data that you have to store. And I think we're one of the biggest, if not the biggest, like S3 storage client in the Nordics. And then once you've kind of the match has been uploaded, we've done our processing, then you can access kind of the analytics of the match. And as you can see here, you have a nice editor that you can go into, and you can get different statistics about your game, like shot maps or pass strings or 2D heat maps, or where was your attacking and defensive line. So a bit more broadly, these are kind of the products that we offer. On the match day, you obviously have the camera where you can do your recording. You have the live app where you can stream to either YouTube or our own live app. And then post-match, you have a couple of social features like the clubhouse and the league exchange. But I think that the ones that are kind of, so those are more social aspects. But then we have the analytics package, which we just briefly talked about. Then we have something called Player Spotlight, which I'm going to talk a bit more about later because that's very related to the player tracking. It's a quite new feature that tries to also provide like more specific, more tailored clips and information for each player rather than just like a team in general. And then finally, you of course have the editor where you can go in and actually watch these, both the analytics and the player spotlight ties into the editor where you can go and see the match. You can also create your own clips. You can add comments. You can manipulate the video in different ways and also share it with with parents or players in the team and coaches and so on. So a bit about how AI in general. So the meat of the presentation is really going to be about how we do, how you can do the player tracking in general. But I also just want to briefly mention how we use AI in general at Veo. So can you see the video running? Okay, so you can see this is kind of, if you just had what the camera is recording, you get these two very wobbly streams. And obviously the players seem quite far away because we want to capture the whole field. And this is not really like the user experience you're looking for. Like it's very hard to even get like useful information of this. But this is kind of the starting point of what we're recording. And then we use different image processing and machine learning techniques to turn this into something the user actually wants to look at. Over here you have the camera, you have a recording, you have a left and a right stream, and then we have what we call the follow cam, which is basically an AI model that creates like a virtual camera system that can merge the two streams and then do panning and zooming in the video to make it look like someone is actually filming. And obviously you can render that and kind of render it and stream it directly to the live app, but it will also be uploaded to the cloud. Then we have a big box here, which is just called image calibration, which is kind of all of the image processing we do to make it look nice. But once you've done that, then you have sort of the base package, which is that if you didn't do the live streaming, you still wanna do the follow cam, and then you can get like basic AI generated events. So for football, that would be like free kicks or goals or corner kicks or these like basic events in the match. Then if you have the analytics package, you get a few more features. So you get the player tracking, ball tracking, and you get some more advanced match details. And all of this then goes into the editor for the user to view. So in the end, like probably, I mean, this is not how we present it to the user, but I think this is a quite old video, but I think it's still nice for kind of showing all the different things we're tracking, all the different kind of metrics. So you obviously have the player track, you have a ball track, you have like, the different events, so goal, corner, shot, and so on. And you have a small 2D map here where you can see the players tracked and which teams they're associated with. So this is kind of what you end up with after these initial two images you saw. You can end up with something like this where you can also see the follow cam kind of panning around and zooming and following the action. But okay, let's get into the actual meat of the presentation, which is more about. So I'm going to talk about tracking or player tracking a bit more general. It's not going to be exactly what we're doing at Veo, but it's some of the nice. I think some of the one or two of the nice papers I've been reading, and that takes a nice approach to it, I think. But in general, it's about there's this kind of base paradigm of tracking by detection. So if you look at the figure here on the right, you have a video sequence, and then you have some object detection model that in each frame is able to identify the objects in there. So in this case, we have different persons in the image, but then between the frames, we don't know which detections are associated with each other. So basically which persons are the same in these two frames. So you need some kind of data association between the frames. And that's where the tracker comes in. And this data association, you can use a bunch of different metrics, and it also often depends on kind of what your camera angle is. So if you have, for example, a top view, then spatial positions are very good. I mean, they can obviously still be used if you don't have it. You can use something like how much are your detections overlapping, how far apart in time are they. You can do re-ID, which is re-identification. So basically like similar to what you do with face recognition, like for this detection, we have the pixels inside and we can see how similar, what is the appearance of the object in this particular detection, and we can do a similarity score with the other detections. And obviously you can kind of combine all of these scores if you want, and then Some of the more old school detection matching strategies are that you use a Kalman filter and this Hungarian algorithm, which solves a small optimization problem to kind of take your data association scores up here and find the best solution for, because you could have multiple detections that might have a high score, so then you have to choose between them, and then the Hungarian algorithm kind of finds a good solution to that. And then you can get your final trajectories from that. Or you can go with a learned data association. So then the tracker here doesn't use a heuristic or like a traditional optimization algorithm, but yeah, uses some kind of neural network to learn how to do the data association. And one way you can kind of look at this is that you can formulate tracking as a graph problem. So it becomes an edge prediction problem. So if we have this figure here on the right, you can imagine that these are nodes in a graph, and we have the detection. So each of them corresponds to a detection, and then we have two sets of detections, one for the current frame and one for the next frame. And then we can create all the different edges. So let's look at the yellow node here, for example. It's connected to all the detections in the next frame, and we want to figure out which of these edges is the correct one. That's kind of the basic formulation, but obviously it's not connected to, we don't want to connect it to other nodes within the same frame because, yeah, the object can't appear multiple times in the same frame. And then you can have these different node features. So you could have, like, for example, here I've just put in the positions, but you could also add velocity. You could have this appearance embedding, which is just an n-dimensional vector that describes what the personal object in this detection looks like. And you can have edge features as well. For example, the similarity score is often used, but you could also have, again, how far apart in time are they? How far apart in space are they? And then we use a graph neural network to solve this problem. But then the challenge is that how do we kind of expand this outside of just, two sets of detections like we have here? And how do we handle occlusion? So let's say that this yellow node we didn't, either a detection algorithm didn't pick it up, or the player ran outside of the field, or there was another player kind of occluding this player, but they then reappear in the next frame. We still want to be able to associate it with this yellow node. So one of the, I guess that it wasn't the first paper, but one of the papers that was quite successful in applying this is this learning a neural solver for multi-object tracking. So over here on the left, you kind of start with the same as you have in tracking by detection. You have some frames and you have detections in them. And then you can see there, these frames, we then just create a fully connected graph of this. So the three detections here kind of go into this part of the graph, and the same up here and the same here. And we have a CNN here. And I mean, that's just to show that you can kind of you can generate features from the RGB values of the crop. You can generate, features from that and have it as nodes features, but you also add the other features we just mentioned, like spatial positions and so on. And then you connect all the different detections. So the only things that are not connected are detections within the same frame. But if we take this particular detection, it's both connected to the node in this frame, a detection in this frame, and detections in this frame. And then you can do, again, message passing, use a graph neural network to process that and end up with an edge classification. Then you have to do a bit of post-processing, because you could technically have that one of these nodes, like this, might have a very high probability of being connected to both this detection and this detection, and we only want it to be connected to one detection in each frame. So then you do a small optimization problem to turn these edge predictions into edge classifications that we can then turn into actual tracks. But yeah, there's one problem with this fully connected graph, is that of course you end up with a lot of edges if you have a lot of frames. So if you had 1,000 frames, suddenly you have a lot of edges, and it both becomes a problem in terms of kind of each node receives a lot of information that is kind of redundant, and also of course you get a very big computational problem. So another paper that is called, by the same authors, kind of introduced this hierarchical graph, where, so if you start here on the left in the figure, you have all your frames here, and you kind of slice it into small compartments. So you take the two first frames, and we actually go back and kind of look at the problem the same way that we did in this graph, and just say, okay, we just need to match two detections. And let's say we look at these two green ones. So they each correspond to a detection, and we figure out, okay, we want to match these two greens. We want to, they're part of a track. So then we go to the next hierarchy in the graph, and now this green node actually corresponds to two detections. And the same thing with the green node down here. And so each of these nodes here are suddenly what we would call tracklets. So they have multiple detections in them. And then you have to think about, like, okay, how do we so then you can gradually kind of go to the next hierarchy and build bigger and bigger tracks without having the overhead of having a fully connected graph. But there's of course the problem of how do you get the node features for this one when it's suddenly multiple detections. So normally what you do is that you just do aggregate statistics here. So for something like the spatial position, you can use like the min and max position maybe, and a mean position, or something that describes the kind of movement between the detections. And for the appearance embeddings, you could, for example, do a mean or a max. Yeah, and then one cool thing about this is that this problem is actually similar to this problem. So you can, even though this is at a higher level, you can use the same GNN in each of the hierarchies and share the weights. And this means that you actually get a lot more kind of simulated data, but the network sees a lot more data. And the authors played around and actually found that it was better to share the weights than to have kind of different GNNs at each level. And then what they add in addition is that you have sort of one small embedding that you add to your node that kind of takes into account what level you're at. And then, as I mentioned before, yeah, you have to solve this small, but it's much kind of smaller greedy optimization problem that you have to solve, because you're only going to end up with a graph, yeah, kind of in two time slices instead of this fully connected graph, which takes into account many different time slices. So once we've then come up with a solution, how do we evaluate what a good tracker is? So one of the most used statistics is this higher order tracking accuracy, and it requires you to have ground truth annotations of the tracks. And I'm not going to go like very much into detail to exactly how you calculate it, but it's a combination of the localization, which is if you have two detections, how overlapping are they? Then you have the detection, which is basically just if we set some fixed IOU of two bounding boxes, like we say, okay, if they're overlapping by this amount, then they're a match. And then we use, again, sometimes you'll have multiple detections overlapping, and you use the Hungarian algorithm to solve a small problem. But basically, in the end, you can kind of associate each of the detections, and we count how many of them are correct. And then the final one is associating each detection with a class or an ID. So are we actually connecting to the right identity? And then you can integrate over different matching thresholds. So one matching threshold could be the IOU of the bounding boxes, and you end up with a score from 0 to 1. And one cool thing about this metric, as you can see in this figure here, is so here you have hot A. So if you only did detection accuracy, then something like this track here, where the ground truth track has actually been split up into 4, we get 100% accuracy, because we don't care about we've just matched all the detections, but we haven't given them the right identity. And on the opposite end of the scale, you would get a very low. This IDF1 is like an identity-based measure. So there you get a very low score, but what hot A tries to do is that it tries to make all of these 3 different combinations equally good. So, yeah, so it's trying to not favor either kind of the identity approaches or the detection approaches. And just to give you, so this is as the numbers from the Sushi paper. So I just pulled out the two architectures we're just looking at, and you can see that using this hierarchical graph gives quite an improvement in the hot A score. But obviously so we like this hot A because it's a very nice metric that measures many things at the same time and take into account different matching thresholds. But that's not really what our users care about in the end. They care about how long tracks they get, if we get the jersey number correct, which is kind of our unique identifier for the track, and also I guess the coverage percent is so. If we have a track, how much if you can actually see the player, how much of the time are we actually tracking the player with the correct jersey number associated to them? They don't really care if we improve HOT A by 5 or 10 or not. So yeah, so looking at this a bit more general, what are actually the components that go into player tracking? So this is a quite kind of simplified approach of it, but first you have some player detection of where the players are on the field. You could also add ball detection to this. And then we have a separate re-ID network that takes, so this will give us some crops of the players. Then we have a re-ID network that looks at those crops and give us an appearance embedding, and that goes into the tracker. And we have the same thing with the jersey number detection. So it looks at the crops and tries to detect what jersey number is, can we actually see the jersey number? And if we can, what jersey number is on this detection? And those then go into the tracker. We get the tracks, but then to get a unique ID for each of the tracks, we have to do team association to figure out what team are they on and what jersey number do they have. And when we know what team they're on and what jersey number they have, we can uniquely identify them. Yeah, so I just wanted to show you what this then looks like once you've kind of coupled it all together. Yeah, you can see, so these small dots kind of behind the feet of the player. So our detection algorithm actually looks behind the feet of the player and then does like a fixed crop around that. And you can see how it's following the players around. And this 2D heat map or 2D map down here, you can then see what jersey number is associated with each player, and how they're moving around. But I think this is also just a nice view of how, for example, we have a field in the background here. You have this, it's not always just like one nice contained field. You have multiple different things kind of happening in the image, which makes the tracking a bit harder. You have people running around on the sidelines and stuff like that. Yeah. So yeah, I just wanted, I think I'm just going to show the video to then kind of show how we can use these player tracks to then create what we call a player spotlight. So I hope you'll be able to see this. Oh. Okay, so how this actually works is that if we have the player tracking and we can track all the players, associate them with a team, and associate them with a jersey number, then if we get once we've kind of processed the full match, we'll have a full match of these AI annotated tracks, and we can identify each player by their team and jersey number. And then most of the action normally happens when the player is close to the ball. So we can kind of, as you saw, you could adjust these sliders to say like what your distance to the ball is and how much time, how big do you want the clip to be around that. So you basically track the player, see when they're close to the ball, and then they can get all the clips where they've kind of been in action and I've had actions close to the ball. Yeah. And I think that was actually the bulk of the presentation, but I just wanted to also do a small promotion for something called the People's Puskas Award, which is that FIFA has this Puskas Award, which is named after a Hungarian football player called Ferenc Puskas, and it's awarded by FIFA for the most beautiful goal. But we kind of reason that it's actually not, they only do pro matches, but we record a lot more football games than there are pro matches each year. And it's quite fun to see. So we do a People's Puskas where people can upload their own best goals they've recorded with a video camera. And then people can go vote for one of them. And maybe if we have time in the end, we can go look at some of them. They're quite fun to see, all these kind of Sunday League amazing goals. But yeah, thank you for listening in.